In this video, we're going to start out by talking about another way of writing our vectors, another form, and we're going to do so by using what's called the standard unit vectors. The standard unit vectors, and you can see in the drawing over here on the right, are I and J, and actually eventually we'll talk about a three-dimensional one as well in other classes. There's a K as well. But the standard unit vectors for two dimensionals are I and j, and they're positioned along the x and y axis. I being the unit vector 1, 0. And again, notice I say unit vectors. Both of these are units because they have a length of 1. And vector j being the vector 0, 1. And we can use these two vectors to write each of our vectors in a new form as a linear combination. Any vector, which looks like this, can be written in the form AI plus b times j. This is called a linear combinations of vectors I and j. Follow the steps below to prove that vector AB, which is equal to AI plus b times j. So, and you can do this, but there's a much easier form. But here's how we're going to prove this. Let's go through, and just so I can show you. First off, let's rewrite as the sum of two vectors. So let's given vector v, let's write vector v as a comma 0 plus 0 comma b, because that's what if you were to add those back together, you would get a comma b. Now let's do this. Let's factor an a and a b out. So vector v we can now say is the same thing as a times 1 comma 0 plus b times 0 comma 1, because they are. If you were to distribute that back out, you would get, again, AB eventually. And then substitute, because we know that 1, 0 and 0, 1 is the same thing as what we just found out as I and J. So A times I plus B times J. So each vector now we can rewrite as a linear combination very easily. Again, this is just another way of writing a vector. If you ever see 2, 5 written as 2 times I plus 5 times j. It means the same thing as your x component is 2, your y component is 5, to where I again is 1, 0, and j is 0, 1. So it's the exact same thing. So vector n, negative 7 comma 3, sometimes will be seen written as negative 7i plus 3 times j. Same thing. Now, do not get this confused with imaginary number I. It is not the same I. This I is 1 comma 0 as a vector. It's a unit vector. RS. So now this one gives us endpoints. So first step is we have to write it as component form. So we're going to do x minus x, negative 5 minus negative 9, which gives you 4. Negative 6 minus 8 gives you negative 14. So another way of writing that is 4i minus 14j. So if it's a negative, we're going to put a minus there. PQ, again, 5 minus, or excuse me, let's write it in component form. Negative 2 minus negative 10 will be negative 2 plus 10, which is 8. 5 minus 6 is negative 1. So in linear combination form, that would be 8i minus 1j. And that's it. So just another way of writing these. Okay, now let's talk about the trig form. The same way we had trig form of complex numbers, we also have trig form of vectors. Let's start out with trig form of a unit vector. If u is a unit vector, I only talk about unit vectors right now, then the terminal point u lies on the, well, if this is a length of 1, go back to some basic trig, this circle right here, all these vectors that have a length of 1 would lie on this circle. This circle is called the unit circle from basic trigonometry. Therefore, u, which is the vector right here, if you've got vector u, which is the vector a comma b, can be written as, well, think about this. Each of these points on your unit circle are cosine values and sine values. So therefore, the first component would be an x component, which is a cosine, and the second component would be a sine component, which is a y value. So therefore, or as a linear combination, it would be, the unit vector would be, you can write it as cosine of theta times I. Now, you got to be careful because you're not multiplying theta by I, but the whole thing. And then sine of theta. Let's try that again. sine of theta times j. So there is your unit vector written as a linear combination. So again, if it's a unit vector, then the x corresponds with a cosine, the y corresponds with a sine. Okay, now let's write of any vector, trig form of any vector. Well, it says because every vector is the product of the magnitude of the vector and its corresponding unit vector. So if you have a unit vector, then you can change it back into its normal vector by multiplying by its magnitude, because the unit vector has a length of 1, and then find the magnitude of the vector you're looking for and just multiply them, and it'll have that magnitude. We can rewrite it in the following form. So your vector that you're looking for will be the length of it, the length of your vector times its corresponding unit vector. So therefore, we've got the magnitude times, again, that unit vector was cosine theta, sine theta. And if you wrote that distributed out, that would be the vector, the magnitude of v times the cosine of theta, comma, the magnitude of v times the sine of theta. And that would be your new vector. Or written as a linear combination, let's do it this third way. That vector v would equal the magnitude of v cosine theta. Let me put all that in parentheses times I, plus the magnitude of v sine theta times j. So you could write it in any of those methods. So now let's do it. Okay, an example. Here's what we mean. Find the component form of each vector with a given magnitude and the given direction angle. Okay, so first thing we're going to do is let's find the unit vector that has this direction angle, and that's really easy. The unit vector that has that direction angle would be simply the cosine 60, comma, sine 60. However, that's the unit vector. That would have a length of 1. So how do we find a vector in the same direction that has a length of 8 instead? Well, you just multiply it by 8, and that's it. That'd be 8 times. The cosine of 60 is equal to a half. The sine of 60 is root 3 over 2. Distribute that out, and you get 4, comma, I believe that'd be 4 root 3. And that would be your new vector. So again, what we just did, this vector should have a magnitude of 8 and has a distance, or has a direction of 60 degrees. Okay, now next one, number 6. Same thing. First thing you can do is find the unit vector that is in this direction. Now, 225 degrees, that'd be somewhere right here. It has a reference angle of 45. However, all we have to do is, okay, the cosine 225, comma, sine 225. That would be the unit vector. If you were to multiply that out, or excuse me, work that out, that would give you a unit vector. However, we want our vector to have a length of 20. So all you have to do is simply multiply that vector by 20, and you've got it. So that'd be 20 times cosine of 225. All students take calculus. Both cosine and sine are both going to be negative. The reference angles are going to be 45-degree angles. So that's going to be negative root 2 over 2, comma, negative root 2 over 2. Distribute that 20 out, and that gives you negative 10 root 2, comma, negative 10 root 2. That should, again, have a distance or a length of 20 and a direction of 225. And you do see that if you were to plot that, that would be a third quadrant. Number 7. We need a length of 12 and an angle of 150. So therefore, we're going to do simply the magnitude times the cosine of 150, comma, sine of 150. 150, that's going to be in the second quadrant. Your reference angle should be a 30-degree reference angle. All students take calculus, so sine is going to be positive. So you're going to have 12 times cosine of 150 and sine of 150. We're going to use our reference angle of 30. Cosine is negative. The cosine of 30 is root 3 over 2. Sine is positive, and the sine of 30 is a half. Distribute your 12, and that gives you negative 6 root 3, comma, 6. and that would be a second quadrant vector. And the last one, take your magnitude times your unit vector, which is cosine 340, comma sine 340. Now 340 is not one of our common angles, so what we're going to have to do is actually multiply this out. And now I do want to point something else out that you're doing here. If you were to distribute this would be 30 times the cosine of 340 and 30 times the sine of 340. This corresponds to last, when you were doing polar graphing and all that, this is r cosine theta and r sine theta from polar graphing. It's the exact same thing, to where this is your radius and this is your angle, r cosine theta and r sine theta. So it's very closely connected to what we've been doing. When you multiply these out, and again, this will have to be done on the calculator, you're going to get 28.19, comma, negative 10.26, which again is located in the fourth quadrant, which is where 340 is. Okay, next up, let's talk about writing these. Okay, it says write each vector in trig form. So it's what we were just discussing. It's like your r cosine theta and r sine theta, or I'm going to actually just write it over here. It was the magnitude of the vector times cosine, and the magnitude of the vector times sine. That was trig form. So first off, we have to find magnitude. So to find the magnitude of vector v, quick reminder, we do the square root of a squared, 15 times 15, that's 225, plus b squared is 64. That's the square root of 289, which is 17. So that was actually a triple. That's an 8, 15, 17. You also need an angle. We know that the tangent of our angle will be b over a, 8 over 15, and you can sketch yourself a little triangle to figure that out. And that means that theta would equal about 28.07. Now that's our reference angle. However, we are in the first quadrant, so we can use our reference angle. So our vector can be written in trig form as, again, r cosine theta, r sine theta is what we're doing, or 17 is the magnitude in this case. The magnitude times the cosine of 28.07, and the magnitude times the sine of 28.07. And that is trig form. Let me zoom in a little bit more, and let's do it again. First off, let's find the magnitude. There we go, so we can see it really good. The magnitude of vector m is going to be the square root of a squared, that'll be 9 times 2, which is 18, plus b squared, which is 6, that's going to be the square root of 24. That splits into square root of 4 times the square root of 6, so 2 root 6. Now let's find our angle. Now we got to be careful. This is a third quadrant angle. Let me put a 3 up here. So let's find our reference angle first. I know that the tangent of my reference angle will be b over a, which is the square root of 6 over 3 root 2. Let's rationalize that, or actually we can divide that. Square root of 6 divided by the square root of 2 on bottom is root 3 on top, and you're left with a 3 on bottom. So that's one of our common angles. And again, all I did there was divided my square roots. Root 3 over 3 as a reference angle, that's going to be a 30-degree angle. So that's reference. However, this is a third quadrant angle. So we have a third quadrant reference angle, so that's going to be 180 plus the 30. So we have a 210-degree angle. So my trig form will be, this vector will equal the magnitude, which is 2 root 6, times the cosine of my angle, comma, the magnitude times the sine of my angle. There is your trig form. Number 11. This one we've got written in a different form. We got it written in linear combination form. If we want to write it as the other form, that's negative 1 comma 7, same thing. So therefore the magnitude of P is going to equal the square root of negative 1 squared plus 7 squared. So that's going to be root 50, which is the square root of 25 times the square root of 2. Next up, we need an angle. So we know that the tangent is equal to b over a, which is 7. We are looking for a negative 1, 7. That would be a second quadrant angle. So let's do the inverse tan to find our reference angle. And I get 81.87. Again, that's a reference angle. We need it to be in the second quadrant. So what we're going to do is do 180 minus that reference angle. And I get a 98.13 degree angle. So my angle is 98.13. So now we're ready to go. So we have trig form is going to equal our magnitude, which is 5 root 2, times the cosine of 98.13, and 5 root 2 times the sine of 98.13. And again, if you were to multiply that out, if you were to multiply that back out, what would you get? You would get this exact same negative 1/7 back. Okay. The next vector is negative 2, 2. So first up, let's find our magnitude. And this isn't written in linear combination form, but you can go ahead and work it out from there. The square root of a squared plus b squared. Again, here's your a and b. So that's going to be root 8. Now we could have treated that as that's a 45, 45, 90. So if you have lengths of 2 and 2, then your hypotenuse is going to be 2 root 2, or your magnitude, because of that being a 45, 45, 90. Next up, I just kind of let you in on the secret. You already know what your angle is going to be, but I'm going to go ahead and work it out anyway. We know that the tangent is equal to 2 over 2, so tangent is equal to 1, so that means my angle is a 45-degree angle, like I just said. However, we are in the second quadrant. Negative 2, comma, positive 2 is going to throw us in the second quadrant, so I'm going to do 180 minus that, so my directional angle is actually 135 degrees. So therefore, my vector is going to be the magnitude, which was 2 root 2 times the cosine of 135, comma, the magnitude times the sine of 135. So there is your trig form. Number 13 gives us a vector with the initial and the terminal points. To find our actual component form, we do again x minus x, negative 9 minus negative 1 will be negative 8. Y minus y gives you negative 4. So there's your component form. Your magnitude is going to be the square root of a squared plus b squared, which is root 80. Let's split that into the square root of 16 times the square root of 5. So there is your magnitude. Now we need a direction. We know that the tangent of my reference angle will equal b over a, which is 4 over 8, or a half. So let's do inverse tangent of a half, and that tells me that my reference angle is equal to about 26.57 degrees. However, we are in the third quadrant. Negative, negative would put you in the third quadrant. So this is my reference angle. So I've got to add 180 to that. And my directional angle is going to be 206.57 degrees. So then now I have my magnitude. I have my angle. So therefore my trig form is going to be magnitude times the cosine of 206.57. And the magnitude times the sine of 206.57. And again, there is your trig form. And one more of these. Again, they give you the initial and terminal points. Subtract your x's, give you a 2. Subtract your y's, negative 8 minus negative 2 gives you a negative 6. So therefore, your magnitude is going to be the square root of a squared plus b squared, or root 40. That's going to be the square root of 4 times the square root of 10. There's your magnitude. Your direction, we know that the tangent of our reference angle will equal b over a, which is 3. Find the inverse tangent of 3, and that gives you a directional angle of about 71.57 degrees. However, let me erase that. We are in the, let's see, 2, negative 6. That'll be right and down. That'll be a fourth quadrant angle. So what we've got to do is find a fourth quadrant directional angle that has this reference angle. So do 360 minus that, and you're going to get a directional angle of 288.43. So there is my actual angle that we're traveling in. That's fourth quadrant. Here is my magnitude. So my trig form will equal the magnitude times the cosine of theta, so 288.43. Or again, you can think of it as last chapter would be r cosine theta and r times the sine of theta, which was 288.43. And there is your trig form.